My name's Fabian Renn-Giles. I'm a C++ consultant and freelancer. I mostly do real-time audio stuff in C++, but here I ventured out into a bit of territory that's normally not my day job. So I'm going to be talking about a semi-compile runtime map with nearly zero overhead lookup. So I only have half an hour, so if you could please ask the questions at the end. I've put numbers on all the slides, so you can just write down any slide you have a question, and then I'll answer all the questions at the end. Okay, so a while back, I was writing a big C++ Java wrapper. And what this did, it created for every Java class I needed, it would create like a little thin C++ wrapper class. And some of these methods, they were called in a tight loop, right? So the right-hand side, this get method thing there, had to be as fast as possible. Now, it turns out loading a method with Java and C++ is actually really slow. So as any good C++ developer will tell you, you should use some sort of cache, which I did. I used an unordered map. Now, that was OK, but there's still some overhead, right? That try and place is going to have to calculate the hash of method name. And I had thousands and thousands of Java methods, so there were some collisions expected. So can we do better somehow? Well, if you look at the original code, in 99% of the cases, my getMethod function was called with a string literal. So that means in 99% of the cases, it was already clear at compile time what the hash code would be. Or even better, it would be clear exactly where in the map this value would be placed. Sure, there's the 1% of cases where, I don't know, somehow through user input, the method name could change, and you would have to look up the name at runtime. So I thought, well, somebody must have created a hash map like that, right? Where the lookup is at compile time, but the values still live at runtime. So I checked, right? So there's Ben and Jason's famous constexpr-all the things talk, where they introduced this CX map type. And if you haven't seen this talk, go see it. It's a really, really good talk. So in this map, all the methods are marked constexpr. And that's great, but the problem is that all the values also need to be known at compile time, right? So this would not work for me because I can only resolve Java methods at runtime. There's no way for me at compile time to somehow magically know what those Java methods will be. Louis, at Meeting C++, he also introduced a map. He used it with an example with an event system. And that map nearly did exactly what I wanted, right? It looked up the values at compile time. You could still modify the values at runtime, but the lookup happened at compile time. You could also fall back to runtime lookup in those 1% of the cases where the key somehow comes from the user. But as you see in the constructor up there, you needed to know all the keys in advance. And for me, that was an issue because I didn't know which kind of Java classes the user would be wrapping, so I did not know which methods they would call. I could not have a single line with all the keys that I needed. So I decided to roll my own. I called it semi-map. Just to reiterate the requirements, we want the lookup to happen at compile time. So where the values are stored in memory, that should happen at compile time, but the storage, modifying those values, should be possible at runtime. If the key is something coming from a user, let's say from std_in, then we want the lookup to happen at runtime. And I don't want to know I don't want to have to specify all the keys in advance. Okay. So the basic principle is super, super easy. You can get such a map, I claim, with a single line of very simple C++ code. So underneath these question marks is a map with integer keys, and the values are strings. Can anybody tell me what that C++ line of code is? Oh, yeah? Array? Yeah, well, array would be like, I would need to know the maximum number of keys. Here, I don't even need to know the maximum number of keys. The address of the string? No. Well, remember, it has the keys, like it should figure out the storage at compile time, right? That's important. Topple? No. Nope. Okay, I'm just going to say it. It's a templated global, okay? I mean, right, if you give it some kind of template parameter like 5, it's going to generate a new global for you just for that template parameter. If you give it 6, it's going to give you another one. If you give it 5 again, it's going to give you the same one as before, right? So this is the basic principle of my map. It's surprisingly simple. Okay, so what about the template parameter? Which keys can I use? Well, the standard says any non-type template parameter will work. So essentially bool, all the integer types, I think pointers, null pointer will work. And with C++20, any class type will also work as a non-type template parameter. So that will give me any compile time literals like string literals or even user-defined literals. But sadly, it's still 2018 and there's no compiler out there that supports this yet. So how do we support more key types in 2018? So instead of using a non-type template parameter, I'm just going to use a type name instead for a moment, right? And I'm going to try to write a magical function which takes a key, and depending on what that key is, it will always return a unique type. And then we can use it like this, right? We can just, put foo into key to type. That returns a unique type. We take the decal type, and then we just pass it to that global variable. Now, for some of you experts, this key to type thing will be obvious how to implement it, but I'm going to go through it anyway. I think it's quite fun. But if you just look at that key to type, it's kind of strange, right? Like we're changing the function signature depending on which parameter value goes in, okay? Is it even possible to write this in C++? Okay, so let's try. So here's my key to type function, right? It's got to be evaluated at constexpr evaluation. We don't know the return type yet. It depends on the parameter. So we're going to let the compiler deduce the return type. And then we just pass this key parameter as a non-type template parameter to this dummy struct, right? And just return that. So that means if I put in 5, well, it returns an instance of dummy t5. Okay, it turns out it doesn't work, right? It's a compiler error. Key is not a constant expression. You cannot evaluate key in a constexpr context like that. But there is something you can evaluate in a constexpr context, and those are constexpr lambdas. So instead of just passing in the key like that, you pass in a constexpr lambda, and then when you want to use your map, instead of passing in 5, you pass in a constexpr lambda which returns 5. So this compiles, this works nicely. We can also put in a nice little macro there to make it a bit more beautiful. We still haven't gained much though, right? Because we're evaluating this lambda here, which is still a non-type template parameter, so we still are restricted to only integer types, bools, etc. We still can't do any strings or arrays. So to do a string, this in fact also works with an array, but I'm just showing a slide for string. We're going to invent this new function called string to type. It evaluates the lambda and then executes the subscript operator on a bunch of i's that I specify with a template parameter pack, right? So maybe at 0, at 10, at 11, whatever. But then we have this nice STL function which helps us generate a consecutive sequence of template parameter integers from 0 all the way to string len. So that means if I put in the key foo into my key to type, it actually returns an instance of dummy t where the template parameters are now f, o, o. Okay, so let's put this all together. Here we have our templated global, right? Down here we have a usage example, and just to reiterate, we're putting in the key conference. We're passing this to our ID macro, which returns a constexpr lambda. We pass this to key to type, which then returns a unique type for every key, right? And we use this as a template parameter to our global. Now, better than a global is to put this into a function and just have a static local, right? This has the added benefit that we can actually specify the value as a template parameter as well. And now we can always wrap this in a class, make this a bit nicer. And instead of all of this boilerplate nonsense down there, we're just going to move this into a nice little wrapper function up here. And now our get method looks particularly nice because it looks like a normal function invocation right there. Yeah. And just for safety, we're going to ensure that when we actually execute that lambda, that it's convertible to the key type. Okay, so all of this code, what's the performance? Well, put it into Compiler Explorer, and you see that when with optimizations on, the compiler absolutely recognizes this is just a static local, right? So it's single machine instruction, and it's just as fast as accessing any global variable. So that's pretty good. But there was one more requirement we had, and this turns out to be quite tough. It's that optional runtime lookup. So it's that fallback if the user does pass in, let's say, a std string as a key, right? Which comes maybe from the user or for something else that you calculate at runtime. So how do you do that? Turns out you can't use that key to type thing because, as we said before, the signature depends on the key, right? You can't like magically create new functions at runtime. So we can't use that. We can't use our get method either because the lambda has to be a constexpr lambda, right? So can't use that. We could have a nice little switch-like statement like this, but then we would need to know all the keys in advance. So that doesn't work either. Oh, I'm too far away from my computer. So the solution is to basically maintain a runtime map of key values, of pointers pointing to my static local storage at runtime, okay? So every time I access a value in my map with get and I use a compile time string literal as my key, I basically add a pointer to my static local storage to the runtime map. Now, this would completely kill performance, of course, because that would defeat the purpose of this talk, right? Because every time I'm executing a get, I would have to, would always add it to the runtime map, which is exactly what we wanted to avoid. So what we're going to try to do is, if this is executed for the first time, we're going to add it to the runtime map. Now I'm going to go on a bit of a diversion here, but I'm going to come back to this, so bear with me just a moment. Let's go back to the original code, okay? Here we have our static local. So what's the compiler actually doing when it sees the static local? Well, one, it's going to create storage for the static local. And second, if you're going to access this value for the first time, it's going to call the constructor. So we're going to make this a bit more explicit. We're going to, first line creates the storage for our static local, and the second line, the first time you execute that line, it's going to invoke the constructor via placement new, okay? Now, this does not change the code whatsoever, right? The assembly is the same. I've tried this with any compiler. We haven't changed the program at all. But I know what you are thinking. On my slide, there is a reinterpret cast. And we're at CppCon, and I'm putting a slide with a reinterpret cast at CppCon. That's screaming undefined behavior. Where are the pitchforks, guys? Well, I was thinking about this a lot, and I was really, really aggravated about this, because this is a really elegant solution for a later problem. But can't use reinterpret cast. And I was like, well, why? I mean, normally you want to avoid reinterpret cast for undefined behavior because it will cause some kind of alignment issues, right? But I'm specifically telling the compiler to align the storage correctly. Another reason why reinterpret cast might cause undefined behavior is aliasing, type aliasing. But if you look at the code, I'm never accessing the storage as a char array. I'm just using it for storage. I'm always accessing it with the same type. I'm always accessing it as a value. So there's no type aliasing involved. But, standard is merciless. This thing is undefined behavior. There is a reinterpret cast. And this is really true. I was thinking about this for days, and then I woke up in the middle of the night. I don't know what I dreamt before. It must have been something really crazy. It was complete in the middle of the night, and I woke up and my first thought was, wait, there was this really crazy function that someone dubbed the most obscure function in C++17. I should look that up. And indeed, that function is called std-launder, and it's used to avoid undefined behavior in exactly these cases. Someone called it on the internet the most obscure function in C++17. And actually, CppReference.com shows pretty much my example for std-launder. And it gets rid of the undefined behavior, but it's basically a no-op, right? It just hints to the compiler that no aliasing is going on here. Okay, so back to my talk. We have this line which will invoke the constructor the first time you reach this line. So let's make this more explicit again. So we're going to have a nice little needs init bool flag, and if that's true, we're going to initialize it and set the needs init flag to false. Now, obviously, I've gotten rid of thread safety here, right? But I'm not claiming that my semi-map is thread safe, just like any other STL container. If you want to make it thread safe, it's quite easy. You can add some locks, but I want my map to be as fast as possible, so I'm not assuming thread safety. And with this bool, I'm actually getting rid of those lock guards if you use a static local. And just to make performance a bit better, I'm going to also tell the compiler that, hey, well, this needs in is going to be false most of the time. It's only going to be true the first time you access this. Okay, so let's look at this initialize method a bit closer. This initialize method it's the only thing it should do is call the constructor via placement new. We already saw that. But now, and this is now back to our optional runtime lookup, we have a convenient place to add it to our runtime map, okay? Now, I'm adding it as a unique putter, and I have to be a bit careful because unique putter will also destroy the storage when it's destructed. And the storage is it had static storage. So we're going to have to tell the unique putter to use a custom deleter, which should only call the destructor. And while we're at it, we're also going to set the needs init back to true. So the next time you want to access that value with a compile time key, it will reinitialize the value. Okay, now runtime lookup is super, super simple. You just use that runtime map and look it up. I've glossed over a complicated issue. I'm assuming here that you're always going to access the value with the compile time string literal first, and then via a runtime key. It's easy to do the other way around as well. I'm not presenting it here because it's not very interesting, but it can be done, and you can just look at the code how to do that. And it has an additional benefit. It's because now we have this runtime map, which is a map of unique putters. We can easily remove values from our map. Even if they were accessed only at, with compile time keys, we can remove them because our unique putter destructor, deallocator, that value deleter thing, will set the needs init flag to true again. So the next time you access it, it's going to be a clean slate. That's cool. Well, performance, we've degraded it a bit. There's a compare now there, right? We have to check if needs init is true or false. If it's false, it's just like accessing a global again, no problem. If it's true, well, then there's going to be loads of code executed, but who cares? It's only the first time. It's not a problem anyway, especially if you're using it as a cache, right? A cache assumes that loading this the first time is going to take long anyway. Okay, but everything is static, right? That's the whole principle of my thing, right? I'm using static locals. So all my methods in that static map have to be static because I'm using it with a static local. So that's not very good because I don't have any per instance storage. Well, first answer to this is, do you really care? If you're using it as a cache, well, then you're probably going to use it as a singleton anyway. So there you don't really mind that it's completely static. And there's no runtime issues because you can clear all those things. You can start with a clean slate again by calling that clear method. So that's not a problem. There is a tiny technical problem, is that if you have completely two unrelated parts in your app using that static map, and they happen to have the same key value template parameters, they will all of a sudden share their values, right? Because everything's static. If you use exactly the same type, they will just share their values. And to get around that, you can just use some kind of like local tag struct to avoid that problem. But I really want a non-static map, okay? So is this somehow possible? Well, let's look at this example. We have 3 instances of a map, which maps a string to an int, right? And these 3 instances, well, they happen to have some of the keys are in common, right? That height key occurs in instance A and occurs in instance B. Now, we can draw this example like this, but we can also say, hey, let's take all of our keys that occur in all of the maps and put them on the left-hand side, and then each key now points to a map saying, mapping this pointer to the value. So for example, for height, I'm saying, well, that height key occurs in instance A and instance B, so let's put a map that maps to this pointer. If it's instance A, it's going to return 67. If it's instance B, it's going to return 178. So I'm kind of like inversing that graph that you just saw. So the advantage of this is that all of these keys, they don't depend on any of this parameter anymore, right? It's basically like a static list of all the keys in your application. So that's great for our static semi-map because that's always static. So let's take our static map. Instead of putting a value here, let's put a runtime map, which maps this pointer to the value. Now we can create a new type just called map. It's no longer static. It no longer has a static get, right? This is now non-static. And internally, it's using one of these static maps. It's going to, with the lambda, it's going to look up, with the lambda, which is a key, it's going to look up the runtime map. And with this pointer, it's going to look up the value. Well, doesn't that defeat the whole point of my talk, right? I'm using a runtime map again. Well, not always. Calculating hash from an address is of course much faster as calculating hash from a string or whatever more complex type. So in these cases, this version is still faster. But I think more importantly that you normally have, well, it depends, but like especially for caches, you normally have only a few instances of a cache, but many, many, many keys. In my case, for example, I only had one cache, right, and then thousands of keys. You know, maybe you have 2 or 3. It depends on your application. But if you only have a few instances, then this version is still faster. Okay, so let's look at some benchmarks. So on the y-axis, I've got the time it takes to access an element in a map, and it's a map that maps strings to ints, and I'm accessing it with a string literal. Okay, and at the bottom is the number of keys. Here we have std map. Then we have unordered map, it's constant complexity, and the static map, boom, is way down there, right? It's basically nothing. It's a single machine instruction. Now there's overhead if you're using a non-static version, so if you can avoid it, use static map, because if you're using the non-static map, you still have that little runtime map there, right? But the nice thing is I'm using a std map for that map that maps this pointer to the key, which is faster for small number of instances. There's still a benefit, right? The more instances you add, it gets a bit slower, but it's still faster than your other maps. As often with these constexpr things, there's a bit of a downside though. Compile time is not so good. I mean, it's okay, right? For my application, I'm in the range of 1,000 to 10,000 keys, which is 1,000 keys on my machine. I don't have a particularly good one. Is around 20 to 30 seconds. So, you know, if I have 10,000 keys, you might wait 5 minutes, something like that. But if you're expecting many, many more keys, then, well, probably not the solution for you. Depends. Okay, so that was my talk. You can find the code there. It works with the Visual Studio compiler, with Clang, with GCC, and there's many more methods that I didn't show here in that code. Thank you. Questions? Questions? Yep. So the question was, did I observe that compile through with both Clang and GCC? I couldn't get it to run with really high stuff with GCC because the memory usage. So that, I don't know.
My question was between Clang and MSVC.
Oh, no, I didn't try MSVC. Yeah, okay, I should try that. Yeah, thank you.
So around page or slide 30,
right.
You're sticking your value into a char array. You're talking about reinterpret cast.
Right.
I'm wondering, why didn't you have like a wrapper type, and then in the wrapper type in the constructor you could do something?
Yeah. So there's several reasons for that. So the wrapper type, it's better to have. Wait, where is this? So the problem is that I said that it depends on which order you access them first. And if you access them with a runtime key first, it has to temporarily live on the heap, your value. And then once, the first time you then access it with a compile time literal, it then moves it into that static local storage. That means there are 2 different constructors that could be invoked depending on which case it is. And then a value wrapper becomes very unclean, right? Because you have a value wrapper, you somehow want to member initialize your value, but you need to, in one case, need to use the move constructor. In the other case, you need to use the default constructor. So that's why that didn't work out.
Thanks.
Any other questions? Okay. Thank you.